same network segment to communicate. If not in a network segment, PC will find its gateway. Let the gateway help it communicate. So it is equivalent to realizing forwarding across network segments. Okay. Now we are officially learning ARP. Now there are several problems in the whole picture. First question. How did the PC find the gateway? Second question. How does the gateway send data from network segment 1.0 to network segment 2.0? This is at the routing level. When we talk about routing, we will talk about. Secondly, for data encapsulation. We all know the 7-layer reference model. Each layer must be encapsulated. Then PC1 sends data to PC2. No matter what happens on the upper floor. If you are doing 2-layer encapsulation, how are the source MAC and destination MAC packaged? Actually, this will involve the knowledge we are going to talk about today, called ARP. Okay. For 2 devices, we first reconfigure it with an address 1.1.1.1, 24-bit mask. The device on the right is the same. We first configure a network segment 1.1.1.2, 24-bit mask. Then, let's capture packets here. When you install this, Wireshark will also be installed together. It's a software for dummies. Very simple. Open Wireshark. This is a software that captures packets. In the future, when 2 data communicate, need interactive message. PC1 has to send data packets out of this interface. When PC2 replies to the packet, packets must be sent out from this interface. Packet forwarding. Then all data flowing through this interface in the future. If you capture packets on this interface again, can be captured. For this interface, no data yet. So no data has been captured yet. When we encapsulate data, I want to ask you a question. I draw a simple diagram here. For example, 2 PCs communicate. 1.1.1.1, 24-bit mask. Communicate with this 1.1.1.2. Then to package. Let's not talk about the upper. Let's look at the second and third floors. Suppose this is a 3-layer encapsulation. The front is a 2-layer encapsulation. We will also talk about the process of data packet forwarding today. Let's start now. For 3 layers, we are blocking the source IP and destination IP. Access destination IP address from source IP address. That is, from 1.1.1.1 to visit 1.1.1.2. So how do you know? Are you going to visit 1.1.1.2? This thing is very simple. Future. When you access data, now the application layer generates a data seal layer by layer to the network layer here. How do you know the IP of the peer? When we go to ping. In fact, ping is suffixed with the other party's IP. Data encapsulation. Now ping this is effectively equivalent to specifying the. It will populate this field. If you visit some services on the public network, for example, you visit Google, then it's all based on. Now the DNS on the device will help you complete the domain name resolution. You are in the corresponding application. When visiting the corresponding address, it will automatically fill in here. So, we don't need to care about the destination IP. We can generally perceive based on the upper layer. That is, transport layer or application layer. We don't care about the 3-layer encapsulation. Let's take a look at the second floor. For the second floor, we must have source MAC and destination MAC. So let's say my source MAC is AA. My target MAC is BB. Then the source MAC AA is already known. But the question is, how can we know the destination MAC? For 3 layers. I can ping its IP. But we're not going to ping a MAC. If I don't know the destination MAC, I can't do data encapsulation now. Just can't ping. So now we need to get this parameter. We're going to make an inquiry. So it is necessary to use the ARP protocol to achieve. This protocol is called Address Resolution Protocol. It's simple. In one sentence, it is known IP to find MAC. Now we know the IP address. 1.1.1.2. Now ask for the MAC address it corresponds to. This is ARP. Now I know the IP of the peer. Hope to get the corresponding MAC address. So to make the corresponding data request. Then please note. Before future requests to the destination MAC address, real data cannot be sent. Like now. Here we are. It is the captured data packet under the right interface of the PC. I'm going to ping PC2 now. That is. Ping 1.1.1.2. For now. After the ping is sent out, the data can be captured here. Then when the data is captured as a whole, we'll look at a parameter. Now PC1 sends data to PC2. The content of the data in PC1 is a broadcast. Encapsulation via ARP. Encapsulated is an ARP packet. Now the problem is, who has 1.1.1.2? I sent a ping. Ping actually uses the packet encapsulation of the ICMP protocol. But you will find, before the ping succeeds, an ARP is sent first. After sending ARP, this thing returned the packet back to it. 1.1.1.2 is at. Behind this is a MAC address. That is. 1.1.1.2 is on the MAC address next to it. This is PC2. Everyone must first know. When we communicate data as a whole, before A sends real data to B, it must first be able to encapsulate the MAC address. Then before encapsulation is complete, they cannot communicate normally. What is encapsulated here is an IP. But everyone should know. Up to the IP is the 4th layer. TCP and UDP. Further up is the data encapsulated by the application layer. But because the encapsulation cannot be completed here on the 2nd floor, so now it is impossible to forward data normally. Then what we have to learn about ARP? It's actually another message. Everyone should know this. In the ARP packet, and no other headers above, it has only 2 floors. Above the 2nd layer is an ARP layer. For ARP, we usually say it is a layer 2.5 protocol. That is, this is our 2nd floor. Generally speaking, is E2. Such a packet encapsulation. There will be 4 contents in ARP. The first one is called sender IP and sender MAC. That is, for the current data, to mark the MAC address. Further down there is a target IP and target MAC. Now PC1 is going to ping PC2. But it doesn't know about PC2's MAC. It will send an ARP packet to ask. Sender IP is PC1 itself. 1.1.1.